right, we're going to continue working in our unit on exponential functions. We've done a lot of work with kind of rules of exponents, simplifying and evaluating, but now we get to what I think is the good stuff. And we'll actually look at some examples of exponential functions. We'll make some graphs. We'll try to find some equations from a graph. All right, so the basic form for exponential functions that we'll be looking at in this class is this: y equals a times b to the x. Okay, and this is our y-intercept. A is, so that's our starting amount. You can think of it like that. How much do we have it when x is 0? And this is our multiplying factor. Okay, and remember that we're not adding a constant amount each time like we were with linear equations. Now with exponential functions, we're multiplying by a consistent amount each time. So b here is analogous to the slope of a linear function, but it's certainly different. It refers to by what factor we're multiplying our y value by each time x goes up by 1. And of course, x is our independent variable and y is our dependent variable, just like normal. Okay, so a quick example here, and then we'll look at some graphs. If you have something like this, that means when x is 0, you have 52 of whatever things you're talking about, and it's tripling each time. So it's actually growing really, really fast, okay? And as you go kind of back in time, x could be -1, -2. As you go back in time, your y value is being chopped into thirds each time, okay? So the base really controls the speed of growth much more than your initial value. Okay, your initial value is important, but the base is much more important. All right, so let's look at a couple examples. First, we're going to graph an exponential function. 1 times 2 to the x. This is probably the most fundamental, most basic exponential function we could work with. And so this means we're starting at a value of 1, and we're doubling each time. Okay, so we can certainly come up with a table. And we could start at even -3, -2, -1, 0, 1, 2, 3. And so we're starting at 1. So where did this 1 came from? It came from that 1 up there. Okay, that's our y value for when x is 0. It's our y-intercept. And I like to just move forward first, sort of down here first before we go kind of back in time and do the negatives. So we're doubling each time. So we have 2, we have 4, we have 8. Okay, but then as we go back into the world of negatives, we have a half, we have a quarter, and we have an eighth. And hopefully you're seeing some commonalities. We have 1/8 here kind of corresponding to the 8 there. Right, so let's go ahead and graph it up. And one thing you'll see when you're graphing exponential functions, for now, we probably will never have negatives in the y dimension, okay? So we'll never be down in this area of our graph. And the other thing is, it's always hard to graph the flatter part of the exponential curve really accurately, unless you do something clever with your scale. But let's just do the best we can and see how it goes. And so I'm just going to go up. Well, let's go up by 1s every 2 squares here, but we'll up by 1s every 1 square here. Okay, so let's have our scale look like that, because we need to get up to 8 in the y dimension. Okay, so our y-intercept is 1. When x is 1, y is 2. When x is 2, y is 4. And when x is 3, y is 8. Okay, so you can see it's getting steeper. So let's see if we can even fit in a 16. If this is 8, 10, 12, 14, 16 would be over here. Okay, so you can see it's getting steeper and steeper as we go. Let's go to the left. -1, -2, -3. And here you just have to do the best you can. You're going to jam some points in real close to the x-axis and do the best you can. And then your last job, I think maybe one of the hardest jobs here, is to see if you can make a nice smooth curve that hits our points. All right, so that's a graph of probably our most basic exponential function, y equals 1 times 2 to the x. So what we just did was exponential growth, and here's some exponential decay, okay? So here we have a starting value of 10, and what's happening each time? We're multiplying by a half or dividing by 2. So we can do the same thing we did before. Let's set up a scale. 2, 3, -1, -2, -3. And we could even do a quick table too. Eventually, unless you're required by your teacher to make a table, you don't need to make a table. You can just go straight to the graph. But let's try -3, -2, -1, 0, 1, 2, 3. And we're starting at 10. Okay, so that's our starting value, our y-intercept. And let's get this guy here. So this means that we have 10 of something, and for some reason it's decaying, it's being chopped in half. We're losing half each time that x goes up by 1. So maybe it's some sort of a radioactive element, maybe it's something we're giving away or losing for some reason, but we're losing half of it each time that x goes up by 1. So we can fill out our table, 5, 2.5, so we're just going to be chopping it in half. But then as we go back in time, we can imagine doubling our y value. So this will go to 20, and then what are we at? 40, and then 80. And so these obviously won't fit on the scale that I've set up, but we should be able to get everything else set up. And I'll show you one trick that we can try as well. So anyway, let's plot the 0, 10. We have a 1, 5. We have a 2, 2.5. And we have a 3, 1.25. So the thing about these guys is, as this decays away, as we get larger in the x dimension, y will never reach 0. Y will get incredibly close to 0. And even if x goes up to 100 or 1,000, y will become a tiny, tiny number, but y will never actually hit 0. And there's a special name for this. We'll probably talk more about this later. But a line, and in this case it's the y-axis or the x-axis, a line that an exponential or a function gets super close to, closer and closer to, but never actually touches, has this kind of silly name, asymptote. So you might hear me refer to the x-axis in this case as the asymptote. It's getting, the function is getting closer and closer to, but never touching it. The other thing I wanted to show you was, we don't really know how steep things are going right in there, because we're not going to be able to get up to our value of 20 for -1. But we could plug in a -0.5. What if x down here is -0.5? We'd go to our calculator and do it. And we get a 14.14. So that's something we could plot. So you can always plug in some decimals as well. Probably in Algebra 2, maybe a little bit in Algebra 1, we'll get into what fractional exponents mean. If you thought negative exponents were counterintuitive, fractional exponents are maybe even more so. But anyway, that'll help us get another point to help us graph our curve. So let's go ahead and sketch it out. And we're going to just get super close to the asymptote here, but we'll never actually touch it. All right, so there's a graph of that guy, 10 times 1/2 to the x. And then our last example for this video here is we are going to determine an equation, and I have it graphed already up for you. So let's find the y values. We can even make a quick table here. We can find some y values for certain x values. So when x is 0, it looks like y is 2. When x is 1, it looks like y is 6. So that's a times 3 right there. Let's see if that continues. When x is 2, for that to continue, it would have to be an 18. And that's a little off the scale, but it certainly looks like it could be an 18 right there. 2, 18 looks pretty looks reasonable up in there. Okay, so we can do it. We have a y equals a times b to the x. Our y-intercept is 2, and it looks like we're tripling each time. So y equals 2 times 3 to the x would be the final answer there. And that's a good place to stop.